Motion and reference frames. Galileo's work Projectiles illustrates the importance of reference frames. He arrogantly supported the idea that the reference frame for discussion motions in our planetary system be the one fixed to the Sun, not the Earth, and that therefore the Earth both rotates on its own axis and moves in a path around the Sun. For many scientists of Galileo's time, this was not an easy idea to accept. If the earth moved, they said, a stone dropped from a tower would not land directly as its base. As earth moves through space, they argued, the stone would be left behind while falling through the air and consequently land far behind the base of the tower. But this is not what happens. So many of Galileo's critics believe that the tower and the earth cannot be considered to be in motion. To answer these critics, Galileo first assumed that during the time of fall, the tower and the ground supporting it were moving forward equally with some uniform horizontal velocity. He then claimed that the stone being held at the top of the tower also had the same horizontal velocity and that this velocity was not affected by the fact that the stone moves vertically upon being released. In other words, the falling stone behaves like any other projectiles. The horizontal and vertical components of its motion are independent of each other. Since the stone and tower have the same vertical velocity, the stone will not be left behind as it falls. Therefore, whether the speed of the earth is zero or not, the stone should land at the foot of the tower. So, the fact that falling stones are not left behind does not mean the earth is standing still. Similarly, Galileo said an object released from a crow's nest at the top of a ship's straight mast will land at the foot of the mast, whether the boat is standing still in the harbor or moving with constant velocity through quiet water. To a sailor standing on the ship, the trajectory will appear to be a straight vertical line in either case. To a person standing on shore, however, the trajectory appears to be a straight vertical line when the ship is stationary and a curved line when the ship is moving. Obviously, the frame of reference of the observer must be taken into account when analyzing the motion of objects. Galileo's explanation of the differing descriptions of the falling object was that the sailor on the deck of the moving ship is sharing the horizontal velocity of both the ship and the falling objects. Sailor, ship, mast, and object are all moving horizontally, so he cannot notice this component of the motion. By contrast, the observer shore does not have the horizontal velocity of the ship and object, and so he can see both the horizontal and vertical velocities of the falling object. These velocities, as we know, add up vectorially to give a parabola. The same ideas apply not only to falling bodies but also to projectiles in general. For example, if a stone is projected vertically upward from a cart, it will fall back into the cart whether the cart is continuously moving at a constant velocity or is standing still. From this and equivalent observation has come a most valuable generalization, usually called the Galilean relativity principle. Any mechanical experiment will give the same result for any observer moving with constant velocity, no matter what the magnitude and direction of the velocity. In other words, it is impossible to tell by any kind of mechanical experiment whether or not one's laboratory or reference frame is really at rest or is moving with some constant velocity. From the Galilean relativity principle, it follows that the laws which describe mechanical experiments are the same in reference frame at rest or in a reference frame moving with a constant velocity. Therefore, the laws for the description of the motion of projectiles would be found to be the same whether these laws are obtained by experiments inside a ship moving with constant velocity or at the dock. Whether on a stationary Earth or on an Earth which, during any mechanical experiment on projectile, is moving with virtually a constant velocity. In all these cases, we are in inertial frames or reference, and we would arrive at a set of equations identical to those formulated by Galileo himself.